Hello there, physics class. We got video 3 for our dynamics week 1 here. So we got free body diagrams. So first question we're going to ask, what is a free body diagram? Basically, what it is it's a diagram showing all the forces that are interacting on some kind of object or people or whatever we're talking about. So let's give an example first of what I mean by that. So let's say, let's do an example of me standing here. Okay, so there's me, Mr. Westwood, standing there. And what are all the forces basically acting on me if I'm standing still? Well, there's only one force that seems like it's acting on me, and that's force of gravity. So we're going to draw that first. There is a force of gravity pulling me down. So force of gravity here. So we're going to go with a mass of 70 kilograms equals 70 kilograms. So how would I find the force on me? Well, if we go back to our simple F equals m times a, I have a mass, and if you watch one of the other videos, you'll know that we actually have an acceleration that's gravity. Okay, gravity is an acceleration. It's an a. Okay, its acceleration is 9.8 meters per second squared. So if I take that 70 and times by 9.8, I get 686 newtons. Okay, force of gravity is 686 newtons pulling down on me. So now that would seem to be the only force around that's actually on me. But if we actually look at this, if that's the only force actually pulling me down, technically then it'd be falling because nothing's holding me up. Where something is holding me up, the ground's holding me up, it is also applying a force to me. And because I'm not moving, it obviously has to be applying the same force upwards. So we're going to do this. We're going to have what's called a force normal. Force normal. And it's the same, 686, because I'm not going here. What does force normal mean? Okay? It is anything holding something up. So basically it's, instead of saying like force of the ground or force of the table or force of anything that you're standing on, a chair, a ladder, any of that kind of stuff. So instead of saying all those different forces, we just call it force normal. Basically I'm standing, not falling through it. That means there's a force normal that's pushing me back up. It's holding me up. And you can say, well, why does that need to be there? Well, let's say I wanted to go stand on a piece of paper that was across, I don't know, across a building or something. There is a tarp. Let's go a little more realistic. A tarp between two buildings. Well, if I step on that, technically the force, like the tarp may not be able to give that same force back up, that's 686, where obviously the ground or a table would be able to do that, okay? So, but this is what a free body diagram looks like. It shows all the forces acting on something. So here we have two. Force of gravity, which is almost always going to be there, and then force normal in this scenario. Let's go with something that's different. Okay, so there's the example number 1. Let's go with something just falling. Okay, so let's go with a marker. And instead of having to draw like whatever object it is, a person, a car, a marker, a water bottle, instead of having to draw all those, we always just in physics draw boxes. So there's a box, that can be whatever we need. That could be a person, it could be a car, it could be a projectile, it could be a marker, anything we need to be. So in this instance, it's going to be a marker falling. So marker falling. All right, let's make this mass 0.5 kgs. Okay, so again, to get the force of that, we know there's going to be a force here, force of gravity, pulling it down. We just score mass times 9.8, so that'll be 4.9. 4.5 newtons. Now, is there anything else if I drop this? Is there anything else actually, like any force on it? We can say no, and in some questions it'll be no. If we wanted to add air resistance, like we are in some questions, you could say, sure, there's force of air resistance. So maybe we draw this. Maybe there's a force of R resistance of like 2 newtons. Okay? So we could add then air resistance if it applies in the question. It'll always be stated like this is air resistance or this is frictional resistance. So There's always going to be that possibility, but if I say something's falling and I say, like, I don't mention any kind of air resistance, we'll just ignore that top part, and then it'll just be a falling object. Okay? So there's our start of free body diagrams. Let's do 2 questions here. All right? So let's go with a new example. Let's just go with this water bottle on the table. Okay? So on these 2 questions, we're going to find all forces, and we're going to find an acceleration if there is one. All right? So on this one, we're going to draw, again, water bottle, and it's on a table. So we have a mass. We're going to say this water bottle has a mass of 1 kilogram. So we have a force of gravity. We need to find an actual force on it. Again, we have an acceleration of 9.8. That's gravity. You'll get used to that as we do this all the time. So our force is also going to be 9.8. That's a horrible 8. Oh well. That's a bad 8. 9.8. All right, I'll make it better. 1 second here. All right, 9.8. Perfect. Okay, so that's force of gravity. Because this water bottle is not actually moving, there needs to be some kind of force that's holding it up. That's the table, also known as force normal. So force normal is also going to be 9.8. So those are going in opposite directions. Force normal equals 9.8. 9.8. So basically they cancel out, and that kind of makes sense. This thing's not moving anywhere. All right, let's do an example where there is actually something moving, and we can actually find out the acceleration. So let's actually go with the same question, but I'm going to be doing this. Let's say I'm now pushing the water bottle with a force of, we'll go with 3 newtons. Okay? So we're going to add a pushing aspect, and that's called a force applied. Okay? Force applied. Force applied. Kind of says exactly what it is. It's just someone applying a force or something. Someone, we'll say for now, could be something, applying a force. So anytime you have someone applying a force, that's just going to be FA. So we're going to do a little drawing here. Force applied, A, equals 3 newtons. So can we actually find an acceleration of this water bottle? So I know the mass of it. It has a mass of 1 kilogram. I'm pushing it with 3 newtons. This goes back to kind of our simple F equals ma questions like answers. And we'll say, well, like, what about all these 9.8, 9.8? Well, these ones cancel out for now. In my next video, I'll talk about net force a little more when they're actually going against each other. For this one, they canceled, so we're not worrying about it. We're just going to worry about this force applied. So to find an actual acceleration, we have F equals mass times A. 3 equals 1 times A. Divide 1, divide 1. And our acceleration equals 3 meters per second squared. So this bottle, when I was pushing it, was moving 3 meters per second squared. So that would be the way to find the acceleration there. So I hope this video helps to start off with just simple free body diagrams. I'll put in a little either PDF or video attachment of someone else as well, just to kind of get the intro of free body diagrams. All right, thanks guys. One more video after this, it'll be good for the week.